Well, welcome to Chem 1. We're moving on now to Chapter 5, which is on thermochemistry. We're going to break this chapter into two lectures. This is the first one of the two, and it basically deals with energy. And I have to warn you that energy is an abstract concept. By that I mean that it's not something you can hold in your hands. Doesn't mean you can't understand it, because in your life you deal with a lot of abstract concepts like the economy or weather, that you see on weather maps that are so common now on your apps on your smartphones. Those are abstract concepts. Energy is abstract in the sense that you can't touch it or feel it, but we use it all the time. It reminds me of the story of a farmer at the end of the 19th century when steam engines, trains, locomotives were coming into being and railroads were beginning to crisscross the United States. There was a farmer who was sitting at a train station waiting on a shipment to come in. He was there with his wagon pulled by a horse, and as the train pulled in, the engineer pulled up and was putting water in the steam engine. And he talked to the engineer and he said, "Tell me about this new fangled device, this locomotive." And the engineer said, "Well, it's not too complex really. You put water here, and we have a fire here, and we load wood in, and then we burn the wood, and the wood boils the water makes steam, the steam goes through the pipes and turns the shaft, which turns the wheels." And the farmer said, "Oh, I get that." So you put wood in there, and the wood is under the tank of water, and it boils the water, makes steam, and the steam moves through the pipes and turns the shaft that turns the wheels. And the engineer said, "Yeah, you got this." And the farmer said, "I just have one question. Where do you hook up the horse?" In other words, in the farmer's mind, that was fine. He could follow what was being said, but to get something to move in his world, you had to have a horse to pull it. So don't be like that. Um, Learn these concepts about energy, and be willing to embrace it, even though it's an abstract concept. So, energy, if you recall from chapter 1, is the ability to do work or transfer heat. Now, we haven't said a whole lot about the details of it until this chapter. Now, in chemistry, we're specifically interested in the energy that comes from a chemical reaction. And so this chapter is about thermodynamics, which is the study of energy and its transformations. The word dynamics means movement or change. So this is thermo, which is heat, and dynamics, which is movement. So this is heat movement. Specifically, the subfield of thermodynamics that we're going to talk about is thermochemistry, which is the study of chemical reactions and the energy changes that involve specifically heat changes in a chemical reaction. And I'll warn you, there are some terms that you're going to have to grasp and master for this information to stick in your head. You're going to have to learn some new terms. So, as we said back in chapter 1, energy, you can think of it generally as coming in two forms. There could be potential energy and kinetic energy. The most important form of energy that we're going to deal with in this chapter is the potential energy in the molecules that are that go into that are in chemical reactions. Um, we're going to label it, as you see here in this slide, we're going to label as EL, meaning electrostatic potential energy. And if this were a physics class, we'd take more time to define this equation, which tells us how to calculate electrostatic energy. Q are two charges, K is a constant, D is the distance between the two charges, and if you multiply a constant times the product of the two charges divided by the distance between them, you get a value for this electrostatic energy. The unit that we most commonly use for energy is the joule. And so if we were calculating energy, we'll get an answer in joules, or if it's a large number of joules, it'll be kilojoules. Now, the um, convention that we use for energy that you have to keep in mind is that um, if two charges, or in this case it could be two atoms or two molecules, if they are far, far, far apart, as shown by this graph, if you move them apart to a distance of infinity, then there would be an electrostatic energy between them of zero. Now, um, in real life, of course, molecules are not infinitely far apart. There's always some measurable distance between them, in our world anyway. And so if the charges, if the particles are of like charge, that is, if they're both positive or both negative and they're close together, they're going to repel each other. And the closer they get, that is, the smaller the distance is between them, then the greater the repulsion or the electrostatic energy. And so that would be a higher value of E, electrostatic potential energy. The further apart they get, the less repulsion there is, so the electrostatic repulsion would go closer to zero. Now, if the particles are oppositely charged, positive and negative, the closer together they get, that is, the smaller the separation between them, the greater the attraction between them. And when the attractive forces are calculated, they're calculated as a negative, and so that would be more negative. If these oppositely charged particles move further apart, the greater the separation between them, that is, then the less attraction there is between them, and so their value goes higher or less negative, that is closer to zero. So you might need to keep those concepts in mind, that very basically like charges repel and opposite charges attract, and the sign convention for oppositely charged particles for electrostatic energy is negative, and for repulsion is positive. Now, when we have oppositely charged particles, as we often do in chemistry, um, so there would be a negative uh, electrostatic energy value. So we're only looking at the bottom half of that chart that we had on the previous page. So when bonds are formed, energy is released. So as two oppositely charged ions move close together and form an ionic bond, then energy would be released, and the value of the electrostatic energy would go lower. Now, if we were to have the ions be further apart, their potential energy would be higher, or their electrostatic energy would be higher, that is less negative. So in terms of thermodynamics, we know that the first law of thermodynamics is that we don't know how to create energy, but we can convert energy from one form to another. And you know this, to heat your home, chemical energy needs to be converted into heat, whether you heat with electricity or with gas. We're converting chemical energy in one chemical form into heat. So with so many solar power devices these days, sunlight is often converted into chemical energy. And there are lots of examples of this, of converting energy from one form to another. When we study energy in this chapter, we're going to have to be very specific about it and get more specific rather than just talking about energy at large. We're going to talk about a system, and a system can be whatever we want it to be. It can be that small part of the universe that we're focusing on. In this case, the chemical reaction is always going to be our system. So if we're reacting hydrogen with oxygen to make water, that's our system. The surroundings, that the beaker that reaction takes place in, or whatever the vessel is, that would be a surrounding. If it's open to the air above that beaker would be part of the surroundings. In the picture shown here, the cylinder and the piston and everything beyond that is the surrounding. The only thing that we're going to call our system are these chemicals that are reacting in the chemical reaction that would be summarized by a chemical equation. So when we're talking about systems, there are three types of systems that your book mentions, and it's important for you to understand these definitions. An open system would be a system where the heat exchange, where the system could exchange heat and mass with the surroundings. In other words, it would be open to the environment. A closed system would be a system that can only exchange heat with the surroundings, but not mass. In other words, it would be like this pictured system, and that's what we'll deal with most often will be closed systems. An isolated system would be a system that couldn't exchange heat or mass with its surroundings. So this picture that we're looking at on this um, page, and it's also pictured on page 167 of your text, is a closed system. So again, the surroundings are the cylinder and the piston, and the system is the chemical reaction that's taking place inside of that cylinder. So there's an important term, maybe the most important in this chapter, which is internal energy. So the internal energy, when we talk about that of a system, is the sum of the kinetic and the potential energy of those reactants or of those chemicals. And we use this E to represent the internal energy. Now, if you ever hear someone talking about the total energy of a system, that's the same thing, internal energy and total energy of a system. One trick question that I've heard often in the past to try to test to see if students understand this term of internal energy is the question comes up: what has more internal energy, an iceberg, a huge iceberg, or a cup of hot coffee? You might think about that for just a minute, and I'll come back to it. What would have more internal energy, a cup of hot coffee or a large iceberg? So generally, we don't know the value of E, the internal energy. We only know how it changes. We can measure that and calculate the change in internal energy. So the sign convention is also important. If you see this, if you can see this small diagram, starting here on the left, we might know the initial internal energy of a system and the final state of the system. Now, in this case, as the reaction goes on, if the final state of the system has the energy of the reactants being, of the products being lower, then the final energy would be lower than the initial energy. And so we would say energy was lost to the surroundings, and so the delta E would be negative. In this case, where the final state of the system has the products having more energy than initially, then the final internal energy of the system would, that is the change in energy would be a positive change in energy. And we'll talk more about that calculation as we move on through this, how we get that positive and that negative as we move on. So back to that question about the iceberg and this cup of coffee. Which one would have more internal energy, an iceberg or a cup of hot coffee? And the answer is the iceberg has more internal energy. Now, it seems counterintuitive, maybe, to some of you, because you're thinking about kinetic energy. A cup of hot coffee obviously has energy because it's hot, and everyone associates, or almost everyone associates, temperature with energy. And that's very intuitive. That's normal to think about it that way. But think about not just the kinetic energy, but also the potential energy. That iceberg, if you melted it down, would make thousands of cups of coffee, the water that is from the melted ice. So in the iceberg, you have a tremendous amount of potential energy and a tremendous mass to boot. So the iceberg would have more internal energy, keeping in mind that internal energy means the sum of not just the kinetic energies, but the kinetic and the potential energy. That's why we say the iceberg would have more internal energy than a cup of hot coffee. Now, when we're talking about delta E, the change in internal energy, delta E, is how we read this symbol, delta E. The way we calculate that is we take the final energy of the system minus the initial energy of the system. So if the final energy is lower than the initial, then of course a small number minus a larger number gives us a negative delta E. That's why we say that if the final energy of the system is lower than the initial, delta E is negative. If the final energy is greater than the initial energy, then a larger number minus a smaller number gives us a positive delta E. That's why we say delta E is positive if the final energy of the system is higher than the original internal energy of the system. Now, sometimes we see these energy diagrams where we graph the internal energy on the y-axis like this. So in this case, if the final state versus the initial state is lower, then of course delta E is negative, or less than 0 or negative. And you'll see these kinds of diagrams in the textbook, and they're just trying to help you graphically see that energy is increasing as you go up or decreasing as you go down. So if the final energy state is lower, it'll be lower here on the graph than the initial state. Now, when we're talking about changes in internal energy, if the change in energy is greater than 0, that means that the final energy was larger than the initial energy. So that would be the case above the line here. So if the system absorbs energy, that means that the final state of the system is going to be higher, or the delta E is going to be positive. Energy was gained from the surroundings, and the internal energy of the system increases, so delta E is positive. If the system released energy to its surroundings, then the final energy of the system is going to be lower than the initial energy of the system. So energy was lost to the surroundings, and the delta E final minus, the E final minus E initial is going to give us a negative delta E. Whenever we're calculating thermodynamic quantities, that is numbers, there's always three parts. There's the number, there's the unit, and then there's a sign. So, the number is whatever the number is. The unit in this case is going to be joules. We're going to calculate energies in joules, or if there's a lot of them, in kilojoules. And then there's going to be a sign, plus or minus. And just to remind you about the sign, a positive delta E results when the system gains energy from the surroundings. A negative delta E results when the system loses energy to its surroundings. Now, with regard to changes in internal energy, when a system, when energy is exchanged between the system and its surroundings, it's exchanged either as heat or as work. So delta E always equals heat plus work. Q is the variable we use for heat, and W for work. If the system gains heat, or if work is done on the system, that is, if Q is positive and W is positive, then delta E is going to be positive. If the system loses heat, or if the system does work, we say it does work, work is done by the system, then energy is withdrawn from the system, and delta E is going to be negative. So the sign conventions for heat, work, and internal energy work like this. When the system gains heat, Q, that is positive, and work is done on the system, then the change in internal energy is going to be positive. There was a net gain of energy by the system. But if heat is done, if heat is added, lost by the system, and work is done by the system, then there's going to be a net loss of energy by the system, and delta E will be negative. Now, if there's a combination of, say, heat gained and work done, then it just depends on the amount of heat gained or the amount of work done. And when we add those up, depending on how big the numbers are, what the bottom line will either be positive or negative, depending on the amounts of heat gained or work done. And we'll do some problems like that with our homework. So we're talking about heat and its exchange between a system, that is a chemical reaction, and its surroundings. So when heat is absorbed by a system from the surroundings, we name that process an endothermic process. And in our lab that we did a few weeks ago, we did some reactions that were, and we classified them as endothermic. Now, if you were holding that beaker in your hand and there was an endothermic reaction going on in the beaker would get cold because the chemical reaction absorbed heat from the beaker, so the beaker would be losing the heat that it was losing into the reaction, so the vessel itself would actually feel cold. When heat is released by the system, that is by the chemical reaction, then the surroundings would warm up and the container would feel warm. So when heat is released by the system to its surroundings, we call that process exothermic. And these pictures here that we're showing on the slide show an example of an exothermic reaction. In this case, potassium plus water making potassium hydroxide and hydrogen gas. Now, usually there's no way for us to know what the exact internal energy of a system is, and finding that value is a complex calculation that we're not going to do in this class. However, we do know that the internal energy of a system is independent of the path that the system takes to get to its final energy state. So, for example, in this diagram below, you don't have to be able to see all this text if it's too small for you to see on your screen. But if we're trying to evaluate 50 grams of liquid water at 25 degrees Celsius and know what its internal energy is, it might have come to this state, 50 grams of water at 25 degrees Celsius, having originally started off as 50 grams of ice at 0 degrees, and the ice warmed up from 0 degrees to 25 degrees. So the ice melted and warmed up. On the other hand, it could have started off as 50 grams of steam at 100 degrees Celsius, or I'm sorry, 50 grams of water at 100 degrees Celsius, and the water cooled off to 25 degrees Celsius, losing energy. In either case, whether it was ice that warmed up or hot water that cooled down, the final state of the system was 50 grams of liquid water at 25 degrees Celsius. And so we maintain that internal energy is what we refer to as a state function. That is, the internal energy of a system depends only on the present state of the system and not on the path by which the system arrived at that state. So whether it was hot water that cooled off to room temperature water or whether it was ice that melted and warmed up, doesn't matter which way it got there. The internal energy is only dependent on the present state or the present conditions of that system and not on the path that it took to get there. Also, delta E, or the change in internal energy, depends only on the initial and the final internal energy, but not on the path that it took to get there. Now, Q, which is heat, and W, which is work, are not state functions. Their values very much depend on the path that they take. For example, in this diagram, we have a battery that's hooked up to a resistance coil, and on the other hand, we have a similar battery, an identical battery hooked up to a fan. Whether the battery is just shorted out with this resistance coil or whether it's hooked up to a fan, over time the battery will be completely discharged by two different methods. And in the one case, the charged battery just loses its charge by losing heat. On the other hand, when the battery is hooked up to a fan, it loses some heat, but on the other hand, it's responsible for making the fan blades turn and doing some work. But the bottom line is that the charged battery going to a discharged battery, even though it went by two different paths, the change in internal energy is still the same change. So delta E, or the change in internal energy, is a state function. It doesn't depend on the path that it took to get from initial state to final state. It just depends on the difference between the initial state and the final state. Now, usually the only work that we talk about in chemistry, the work done by chemical or physical change, is the mechanical work that's associated with a change in a volume of a gas, like we see in this diagram, where we have a gas enclosed in the cylinder and it pushes against the cylinder, or maybe the air is pushing down against the cylinder, compressing the gas, and so there's a volume change. The work that we're talking about is usually the work done compressing or expanding a volume of gas. So we can measure the work done by gas if the reaction is done in a vessel, and if the vessel is fitted with an arm here that goes to a piston, and where the the gases push against this piston to raise it or allow it to lower, and so there's a change in the volume. Now, we always say that this work done, the sign convention is that it's negative. To agree with those sign conventions we talked about earlier, it's work done by the system. Whenever there's work done by the system, it's doing work, so we say that the work done is negative. And we calculate that work by multiplying the pressure times the change in volume. So we have to know, to calculate this work, we'd have to know the pressure and the value for that, and the value for the change in volume. In this case, the reaction, you don't have to have any familiarity with this to understand it, but we're having zinc reacting with an acid, making, we're starting off with zinc metal, making zinc ion plus hydrogen gas. And so the hydrogen gas that's produced is moving this piston upward. In other words, there's an increase in volume. So means that the system is doing pressure volume work. Now, if a process takes place at constant pressure, and when we say constant pressure, what we really mean is at atmospheric pressure. Now, we haven't talked a lot about atmospheric pressure or air pressure, but what you need to know is that when we do chemical reactions in chemistry lab, we're doing them out in the air, in the open air. And generally speaking, you can think of the atmospheric pressure or the air pressure as being constant pressure. It's pretty much constant all over the world. And the only work done is this pressure volume work in this scenario. And so when we have that condition of constant pressure, we can account for the heat flow during this process by measuring a value called the enthalpy of the system. So enthalpy we define as the internal energy plus pressure volume work. When the system changes at constant pressure, the change in enthalpy then is the change in the internal energy plus the pressure volume work that's done. So we write it this way: delta H, the change in enthalpy, that's a new term, equals the change in internal energy plus the work done, the pressure volume work. Now, a word about the signs, the sign conventions. We say delta, we've said the change in internal energy equals work plus heat. Now, work we've just defined as a negative pressure times change in volume. If we substitute these into this enthalpy expression, delta E plus P delta V, what we get is, in place of delta E, we put in this in place of delta E, we put in this Q plus W here, and in place of P delta V, we put in work, and it's negative there. And then, so Q plus W minus W, the W's cancel, and we're left with Q, or heat. So enthalpy, the change in enthalpy, that is equal to the heat of the reaction. So at constant pressure, this only applies at constant pressure, the change in enthalpy is the heat gained or lost by the reaction. A process is endothermic then when delta H is positive. A process is exothermic when delta H is negative. So whenever you see later on in the calculations we'll do a reaction that has a positive delta H, you'll know that specifies an endothermic reaction, one that gains heat. And if you see a negative delta H for a calculation, you'll know that that system lost heat to its surroundings. Now, when we're talking about the enthalpy, or the heat of a reaction, the change in enthalpy, delta H, is the enthalpy of the products minus the enthalpy of the reactants. That's how we do the calculation. So if we were talking about methane or natural gas reacting with oxygen, this would be a combustion reaction to form carbon dioxide and water. We would take the enthalpy of the products minus the enthalpy of the reactants to calculate the delta H for the reaction. RxN is abbreviation for the reaction. This quantity, delta H RxN, is called the enthalpy of the reaction or the heat of the reaction. If we're talking about hydrogen plus oxygen to produce water, where hydrogen and oxygen are the reactants and H2O or water being the products, to calculate the enthalpy of this reaction, we would take the enthalpy of the products minus the enthalpy of the reactants, and in this case, the delta H is very negative, meaning that it's an exothermic reaction. Now, what you need to remember about what we've talked about is that enthalpy is an extensive property. If you don't remember that term, extensive and extensive, extensive means that it does depend on the amount of the material that's there, and enthalpy very much depends on the amount of the reactants. If you have more chemical there, that is more mass, then there might be, if it's an exothermic reaction, it'll produce more heat if there's 2 moles reacting versus 1 mole. So enthalpy is an extensive property. It very much depends on the amount of material that's there. The enthalpy change for a reaction is equal in magnitude but opposite in sign to the delta H for the reverse reaction. Now that's a lot of words to say that if you reverse the reaction, let's say you have a reaction and you know what the delta H is, and let's say it's maybe a negative 800 kilojoules or something like that, negative 800. If you were to reverse that reaction, the enthalpy change for the reverse reaction would be the same, but it would be opposite in sign. So if it was negative 800 kilojoules in one direction, if you ran the reaction in the opposite direction, it would be positive 800 kilojoules. And the third thing that you need to know is that the enthalpy change for a reaction depends on the states of the reactants and the products. In other words, are they solids, liquids, or gases? Later when we do calculations, you'll see it matters very much to determine what the states are, if they're solid, liquid, or gas. That's all that we're going to say in this lecture about this thermochemistry. The second part of this lecture will get into more calculations. So what I would encourage you to do are try to get these terms and these concepts about energy changes in your head and try to become familiar with these terms. And I look forward to talking with you soon about the calculations.